All right, so let's continue with these columns, right? And I was surprised. I was going through the exam and looking at the requirement for the compression bars. And some, I think they were just guessing at the stirrups, but they couldn't find the distance or the spacing of these stirrups in most cases. And this is something that is important because otherwise your bars that are in compression could buckle and push the concrete, so the shells of the concrete, the outside shell, they can push it out. And so that's why there is this requirement for a minimum size of stirrups depending on the bar, on the longitudinal bar, and there is a requirement for spacings. And I thought, I know we mentioned it in the case of the bars in compression for beams, and I did mention that here too, right? So it's the same thing for columns. It's the same thing. These are compression bars, right? So ties must be at least number 3 for 10 or smaller longitudinal bars. A number 11 or larger bar will require a number 4. So this is how you decide on the size of the stirrup. The spacing for controlling this lateral movement, this potential buckling, right, of the bar and trying to hold it in place, are these 3 numbers, right? 16 times the diameter of the longitudinal bar, 48 times the diameter of the tie, and the smallest column dimension. Okay? I think I went through, I would say 70% of the part A, and only 3 people have really used this. Everybody else didn't know what to do. Okay, so don't forget that. I mean, this is also valid for columns, right? And so we have the spacing requirements, and then of course the aggregate requirement here, but that's for the minimum value, okay? Because you need to let your concrete flow through the bars. But it's not just that number. Remember, there are 2 more, right? There is the 1.5, the diameter of the longitudinal bar, or 1.5 inches. But that's minimum. Okay? That's your minimum clearance. And this one is your maximum spacing that you can provide in order to control the lateral movement of the bars. Okay? All right, so that's kind of reviewing that just to make sure that you remember that, because you have to use it. Okay. All right, so now what we learned in the last presentation was the difference between a braced and unbraced frame, or a sway and a no sway structure. Okay. And why is that important? That's important because the formulas to decide if a column is going to be slender or non-slender depends on if it is braced or if it is not braced. Okay? And so that's what we need first to understand that part, and then we can apply the formulas for slender, usually called long columns, and non-slender, usually called short columns. Now, the long versus the short is something people use, but it's not really correct. Okay, I have normally when I do the class, I do a little trick on that, but you can do it by yourselves. Just pick a sheet of paper, right? Put it vertical and try to apply a load to it, a vertical load to it, and you see, it just bends, okay, automatically. And notice that it always bend in the direction where is the weakest. All right. Now, take the same paper, roll it like making a little cylinder, right? And now apply the same vertical load, and you can see now that it holds more load, right? And so the height in both cases is the same, right? So which one is long and which one is short, right? So long and short has nothing to do, or well, not nothing to do, but it's not just the height of the column. Okay, let's put it that way. It's more than just the height of the column, because you can see with that piece of paper, the height is the same. What matters really is also the cross section. Okay, so it's a combination of the height of the column and the cross section. Okay, that's what makes the thing to be either slender or non-slender. All right, so it's height and cross section. Okay? So the term that we use is K times LU over R, and this is what we call the slenderness ratio. So this is your slenderness ratio, okay? K LU over R. So LU, of course, refers to the height of the column, and R is the one that captures the properties of the cross section. All right. So we're going to discuss this more in a minute. One thing though, in the case of the column, notice that I'm not using LC, right? LC is distance center to center, which we use here when we found the Q index, okay? This is the center to center going to the joints, right? So these are the same, the LC will be the same dimensions that you normally give your software, right? These are the joints, these are the location of the joints. So that's where you get your LC. But this is LU. So LU is what we call the unsupported length of the column. Okay? And that one is, for a lack of, I guess, better term, is really a clear value. Okay? So it's the clear value between the floor and the beam, right? So that gives your LU. Now the LU for a given column may not be unique, because if the beams that meet at the column joint in all directions, right, are not of the same size, then you will have an LU in one direction and you would have an LU in the other direction. They're different. Mm-hmm. So that's that. The K value is your column effective length factor. This is something that you should have seen for the first time in mechanics of solids. You took a steel design, you probably seen it there again. Okay. So that's a factor that simply accounts for what portion of that length that you have of the column, right? What portion of that length behaves like a simple, like a column having two simple supports, all right? So that's the intent of the K. So the K is simply an equivalent number, right? That when multiplied by LU will give you the equivalent pin-pin connection of the length of the column. Mm-hmm. Now your load will decrease. I mean, that's something that you probably picked up in mechanics of solids too. As you increase your slenderness ratio, your buckling load, your critical buckling load, will be smaller, right? So the larger this value, the smaller your critical load. Okay, so there is more chances of buckling, right? So columns with large slenderness ratio are classified as slender columns, and their axial capacity may be governed by buckling issues. Okay. And columns with small slenderness ratios are classified as short or non-slender. Okay, so we need to look at what the number is, right? So these are columns that the effect of secondary effects are not critical. Right? They can deform a little bit, but there is no significant increase on their moments due to this buckling movement. Okay? So in the case of short columns, what that means really is that the column actually reaches the strength of the materials before failing. Okay. In the case of a slender column, the column may simply fail and still haven't reached the strength, the maximum strength of your materials. Okay? So that's what is important on this. Mm-hmm. Now, the critical buckling load, which is defined here, again, I expect that this is a term that you have seen before in mechanics of solids. This is your Euler load, or Euler, okay, whichever way you want to pronounce it, Euler load. So that was defined long time ago. So this is mechanics of solids, okay, right there. So notice that it depends on the stiffness of the member, the rigidity term, and there is the length here, right? And then, of course, your slenderness ratio, it is here. Okay? The problem with all this, in the case of concrete, in the case of steel, for example, it's pretty easy, right? You find your modulus of elasticity and moments of inertia, you got it done, right? But in concrete, it's a little bit more difficult. The problem with concrete is that you want to predict this ultimate behavior, right? But this ultimate behavior in concrete includes the cracking of the concrete, creep of the concrete, includes this nonlinear behavior, right? Because concrete is nonlinear pretty much. Right? So all that has to be captured by this EI value. Okay? And so that makes it difficult. Okay? The other thing that we have is that you have to remember that the strength of the concrete is really one order, really, magnitude lower than steel. Right? You would talk about 60,000 psi for steel, but we talk about 5,000 or 6,000 for the concrete. Right? So the cross-sectional area of reinforced concrete columns tends to be bigger compared to the area of one steel member. All right. So we don't see a lot of these buckling failures in concrete columns. Not that they cannot happen; they do happen, right? But they're not very common because of the large cross sections that we have in concrete members. Mm-hmm. So that means that the value really that you have here for critical value is a lot larger than some steel member. Okay, and that's why in steel members, I mean, checking for this buckling load is so important. Okay, so important. All right. Indeed. So we talk about columns with large slenderness being long or slender columns. As I said, I explained the term long is kind of a misnomer, right? But those columns are columns where, in case the structure of the column starts failing, it starts developing additional displacements that will cause additional moments and therefore creates more moments, and this creates more displacements and more moments and so on, and then it fails. Okay. So how do you find these values? How do you decide if it's slender or non-slender? So far we have say large values, but what is large? Well, that depends on the frame being braced or unbraced, and that's why we needed to know that first. Okay, so for columns that are not braced against sideway, okay, so these are unbraced or sway frames, right? This limit is 22. So when KLU over R exceeds 22, the column becomes long if it is a column that belongs to an unbraced frame. Okay. For columns that are braced against sideway or an unbraced or oh, this is not right. So columns that are braced or and sway frames, okay, then the limit is given by this other value. So there is no number. All we know is that it cannot exceed 40, okay? But it depends on the moments that you have at the ends of the column, okay? At the ends of the column. So you need to know your moments at the end of the columns, and that will then dictate the number. So this number then is variable for columns that are braced against sideway. This limit that decides if it's slender or not is variable and depends on the moments, but it cannot exceed 40. Okay, it cannot exceed 40. So K, we already talked about it, is the effective length factor, right? For some of you that are taking taking steel, you've already seen it. You can use these charts, right? And you can find your K value. And notice there are two K values, one for non-sway and one for sway frames, right? And so you need to use the proper chart. That's again the reason why you need to know when a frame is non-sway, when a frame is sway, because the charts are different. Notice that the values here for the K do not go past 1. The values here can go all the way to infinity, theoretically, right? So that's important. Okay? That's very important. All right, so LU, clear distance, right? You already talk about a little bit of that. R, of course, is your radius of gyration. So this is the one that captures the cross-section, right? And the radius of gyration, of course, defined by modulus moment of inertia divided by gross area. It can be approximated as 0.3 h. Okay. There. And let me see if we have something here. I think, because this is your FE. Your FE has a little more precise value, I think. Oops. Let me see. Let me see, they give it to you here. Oh, right there, right? So notice that for the FE exam, you are required to use 0.288 h, okay? Which is a lot closer to the real number. The code allows you to use 0.3, okay? For rectangular sections. And it's a function of h. Maybe see what it doesn't matter. Well, if it's a square column, it doesn't matter. But if it's a rectangular column, you need to decide again, this is something that we've been doing already, right? Which way is going to bend? Which way is the bending? Which one are you looking at? So, because your h will change depending on the direction of your wing load or your earthquake load, right? So h then for rectangular sections varies depending on the direction that we're looking at. And I mentioned this before, the h value is parallel to the direction of your lateral load. Okay? So your H value is parallel to the direction of your lateral load. For circular sections, 0.25D, of course you can find these values. And then N1 and M2, okay, are the moments that you find from your regular analysis, first order, okay, first order elastic, so that's your regular analysis. And N1 is the smallest and M2 is the largest. And some people get kind of work out, I guess, because oh wow, which one is going to be the largest, the 1 and M2? 1 is smaller than 2, right? So 1 is the smallest, 2 is the largest, always. Okay, that's the easiest way to remember this. 1 is smaller than 2, therefore N1 represents the smallest, M2 represents the largest. All right, and then you put in the ratio 1/2. Okay. And this ratio is considered negative if the member deforms in a single curvature, and positive if the member deforms in double curvature. And the reason for this is you have single curvature, that is worst for the effect of being unstable, all right? And so then it has a negative effect, so we make it negative. For a double curvature, no, so your column bends in two directions, like an S shape, yeah? So as a double curvature will be an S shape bending, right? In that case, that is much better for buckling, all right? So then it's positive. One thing of caution here, as you look at previous solutions in the internet, the signs of negative and positive used to be the opposite before 2014. But also this equation had a negative sign here and not a positive sign. So that was changed starting in 2014. So then be careful with those other solutions. Okay, they had to be used with the proper equation. Okay? So the results have not changed. The only thing is that in 2014 they made this value, this sign that was negative, they made it positive, and therefore to keep the same result they had to change the definition of what is negative and what is positive for the ratio of M1 over M2. Okay? And you have done steel probably had the same thing, and so be careful, okay? Because you may have learned it different, and now I'm telling you the opposite. Okay? So single curvature is bad for buckling, therefore is negative. Double curvature, which is an S-shape behavior, is good for buckling, and therefore we want it to be positive. Okay? And so that's what we're looking on this. So again, you taking a steel and you learn it. You learn the opposite thing about this ratio. Be careful. Okay. In there. So let me just show you here a couple things from the internet. I mean, I think you understand that, but for some of you may not. Here are things that behave. Notice how a column here, single curvature, double curvature, all right? And we have several of these examples in terms of what is one and what is the other one. Mm-hmm. And so that's why we are looking at some, that's why we have all these definitions. Okay. So again, this one right here, you can see this is a good one because you have the actual moments shown. Oh, I don't know where it go. Where did it go? Oh. Well, I think this one that I was showing you is also the same. Um, this one, right? So I don't know where it's coming from. Yeah, this is more advanced. I mean, it has a lot of this stuff. But that's not what I wanted to show you. Okay, so let me do this one. Right? Notice here, right? For a single curvature, the moments are opposite. Right? Look at that. Right? Right? For double curvature, the moments go in the same direction at the end. These are the moments at the ends of the columns. So think about these members being columns. Okay? So the moments at the end of the columns, right? If they are rotating in the same direction, will give you double curvature. If the moments are rotating in the opposite direction, it will give you a single curvature. Okay? So that's your double curvature and your single curvature. Right? Okay, so we got that taken care of, I hope. All right. And here are things that you probably learn in steel design, right? You have two fixed ends. Your K value is 0.5, right? What does it mean? It means that the pin-pin connection is half of the length of the column. That's the equivalent. Okay, so the equivalent, this is the one that is, we're trying to make all this equivalent to this one, pin and pin, right? So for this one to be equivalent to that, it means that the buckling length is only half of the beam. Okay, for a beam that has a pin and a fixed, the value is 0.7. So someplace from here to here is the equivalent to a pin-pin connection. Okay? If it's something that moves like this laterally, right, still maintains a 1. This is the flagpole, right, the flagpole effect. So notice that this one is a 2. That's one of the worst cases, right? And that's because this is the pin end, right? The other pin end will be equivalent. You continue this drawing and you continue here down. It will be someplace around here, okay? So that means that the pin value is twice this condition. Okay. So in order to make this one a pin, you had to go twice the length of that member. Okay. So that's why it's worse. This one is also pretty bad. You have something like this and it moves laterally. Yeah, they give you also 2. This is pretty bad one too. Okay. All right. So these are the ideal cases that you normally learn in mechanics of solids. So this you should have learned in mechanics of solids. Okay? But the one we're going to do is not that. Okay, that will be kind of theoretical. You may get some of these in your FE exam, right? Because they want you to find this quickly, right? And so they expect that you remember these things, especially this one, that one, this one, and this one. Okay. They expect that you know that, and so for the FE exam, you will pick these numbers and make it very quick. Okay. But in reality, I mean, you were going to use those charts that I showed you before. Okay. So what is this effective length factor then? It's just a constant that multiply the length of the column to provide an equivalent length corresponding to the pin connection. Okay, that's where your K value is. Okay. All right. And so for cases where you do not have displacement, K values are below 1. For cases where you have displacement, K values are greater than 1. Okay. So that you need to remember. That's conceptual. Okay, that's conceptual. All right. And of course, that means that you have to know again if your structure is braced or unbraced, because that will change your K values, right? Now, the Jackson-Moreland charts, which I show you, are the ones that normally we use in concrete. And as pointed to you, there are two charts, right? So there are two charts, one for non-sway and then one for sway. Okay? So we have the two charts in there, right? So braced or sideway uninhibited, and braced or sideway uninhibited, right? So structures with k values varying from 1 to infinity, which is this case right here, right? The sway case, 1 to infinity. This one, the brace case, is 0.5 to 1. In the case of sway frames, it is recommended not to use k values smaller than 1.2. So you have a sway case and your value comes out to be 1.1 right in here now. And I think you should start with 1.2 and higher, okay? In most cases. That's kind of a practical recommendation for that, right? The charts, of course, were developed for uniform frames, and for special structures you may need to do some modifications. Now these charts are being reproduced here again, and so these are the ones we're going to use to find our k values. So how do we find the k values? We need to find this psi A and psi B value. Okay? The psi value is defined as the columns, so this is the EI over L, right? And notice that here we're using center to center, okay? So careful, okay? So be careful here because we're using center to center values, okay? And there. We are using this EC for on concrete, and we're using the I that we're going to calculate based on recommendations from the code in section 66311. And so if I go there, you will see that since we are already in 66311 right here. Okay, so all right, so we have so 66311 will give you recommended moments of inertia for columns. Okay, and this is what they say: a column moment of inertia should be 70% of the gross value. Beams should be 0.35 of the gross value. Okay? So you should be using these numbers to find your moment of inertia. Okay? Now there is here something in the commentary that for the case of T-beams, right, you can use 2 times the gross moment of inertia of the rectangular portion. Okay? And if that is the case, then you multiply by the 0.35, right? Then you get 0.70, right? Now for the analysis that I'm going to do for frames here, I'm going to treat my beams as rectangular, not T-beams, and therefore I'm going to use 0.35 for beams, and I'm going to use 0.70 for columns. Mm-hmm. Now there is another table that was developed later, is this one, right? This also gives you moments of inertia for columns, minimum value 0.35, and then your maximum value that goes to 0.875 that you can use, and then you have a variable moment of inertia depending on where you are between these 2 points. I mean, it's not a bad equation. It's just that you need to put here your moments and your axial loads, and so there is more calculations involved in this that make it a little bit more complex, because in order to do the analysis, you need the moments of inertia. And to do the analysis, your moments of inertia should reflect these conditions. Mm-hmm. So some of you may be worried now, but you didn't use it in your analysis. I know you didn't, right? But it's not too bad, because in the case of your frames, right, you have T-beams, right? And you have T-beams, that means that this really becomes 0.70. And so this is 0.70 and this is 0.70, right? So we are using the same. When you take the relative ratio, right, the 0.70 will cancel, and all you will have is the gross value for the column over the gross value of the beam. That relative value is what is important for your analysis, because if you change the relative value, you will get different answers. Okay? This is again what you do with the modeling. So modeling is your responsibility. So do you want to have the relative value to be 1-to-1 between columns and beams? That's your model. Somebody may say, no, really I want my beam to reflect more cracking than my column, even though it's a T-beam. Then you will use a lower value for your gross moment of inertia, so your ratio changes. Okay? And the fact that it changes, it gives you different moments. And so you may think that you got the right answers. Somebody else may get a different answer simply because it changed the relative value between columns and beams regarding the moment of inertia. Okay? And for those that are learning structures, which you shouldn't, because for this class you should have already taken structures, but I know some of you manage to always go around prerequisites, right? And for those of you that are doing that, you should be learning that when you analyze an indeterminate structure, the answers that you get will depend on the relative inertia of the members. Okay? So you change the relative inertia of the members, your answers are different. And that's why modeling concrete, it gets difficult. Because you think you got an answer, but yeah, you got an answer, but it may not be the correct answer, because that depends on how much cracking, how much creep, how much shrinkage, all these things that are affecting your concrete, the nonlinearity, and all that are changing your moments of inertia. So you're trying to do the best you can to predict these moments. Okay? Lots of the research programs account for all these things, and therefore they give you a little more precise values. Okay? But the commercial ones, they give you the option, or you can change this, but you're just changing it in an approximate way. Okay? But that's what makes modeling concrete more difficult than modeling steel. Okay, steel is pretty easy. I mean, you go moment of inertia, moment of inertia, moment of inertia. There is no problem, no problem there, right? But in the case of concrete, somebody can come up with so many different types of moment of inertia depending on the amount of cracking, the amount of nonlinearity, the amount of creep. And so that's why getting one value for concrete is a bit more difficult. But still, I mean, we get it within a reasonable estimate for our design. Okay? So the L values here are center to center. Okay, center to center. That's important. And the psi value, of course, varies with the degree of fixity in the foundation. Okay, and so because you need to model also the foundation, right? That's one of the nodes for your frame, right? And so you need to know that because it's a joint. So for the case of the foundation, the psi value will be equal to infinity if you have a pin connection. Okay? Because it can rotate a lot, right? However, we don't use infinity. We use 10. That's kind of a practical number if you have a pin connection. If you have a fixed connection, the psi value is 0. But we don't use 0. We use 1. Okay? Now, here are some practical recommendations for real life. Right? If you have a footing that is anchored on rock, that means really, I guess, better way than anchor would be embedded. Okay? It's kind of embedded. You really have it inside the rock. 1.5, okay, because it's closer to fixed. It's inside the rock, right? Is the footing is just sitting on top, okay, of the rock, then a 3, okay. Footing on soil should be a 5. It's not a 10. It's not pin, but it's not fixed either, okay. So 5. Footing on multiple rows of end-bearing piles. So that means you got these deep piles of drill shafts going down, 50, 60 feet, but you have several that are holding your column, right? In that case, you have it fixed, okay? That's a fixed condition. In practical, so what is a fixed condition? That is a fixed condition, all right? Having these deep piles supporting your column, but going way deep, okay? So that brings here another issue, right? With analysis. Because you're telling me here, okay, wait a minute. They put a footing on the soil, and that's not a pin, and that's not fixed. So how do I model that in my software, right? Okay, some software packages will give you the option to define your supports as different springs. So this will be a rotation spring, okay? And so you will have this spring, and you have to define the properties of that spring. So that way you allow for it to rotate some, but not a whole lot. So then you are more on this case. Right? But what you're doing in your project is fine, because we are not that advanced yet. Okay? I just wanted to let you know that yes, you have learned these things, but there's still more to learn. Okay, it's a lot more to learn, and you are going to assume either pin or fixed. A lot of people do some of that. Most people, you have a footing. Most people will assume the footing to be a pin connection. Okay? Why a pin connection? Because that will give you a 0 moment at the footing. Okay, that's one thing. And 2, the moment at the top of the column will be larger than if you do fixed connections. Okay? And so you have a larger moment, you have a pin connection at the bottom, and not only that, you only have one moment at the end, at the top end, you have one moment, the other moment is 0, right? Because it's pin. What kind of curvature do you have? So when you pick it up, right? That's 1. So it's a single curvature. You only go one moment. So that's a single curvature. So making it a pin connection at the footing and having only one moment at the other end results in a pin connection. So that's kind of the worst condition for this column, right? Large moment, single curvature. Right? So you're being conservative on your design. Okay? So there is no need to panic. You don't have to put these springs and trying to model perfectly. That's ideal. Yes, we would like to do that. But doing a pin connection is reasonable. You're very conservative, okay, and you get a good design. All right. Okay. Other people have worked out, different formulas to come up with these k values, right? And in this case, again, the psi A and psi B the same as before, but they also have a psi minimum, which is the smaller of the two numbers that you got that will go here. Okay? And then you will get this. This will work for braced frames. Then you want unbraced cases. There is this one right here. Okay? Furlong also did this for unbraced cases, where psi m is the average of the two values. Okay? So trying to predict this k value, because the charts, that we have here, again, these charts are now an approximation, all right? If you did steel, you probably apply lots of correction factors, because steel didn't do the correction factors. Concrete, we should, but we don't have many of those cases where they need the correction factors, so we don't use them a lot, all right? But there are correction factors that need to be applied to this. All right, so we have talked about all this. So now, what do we have then? A summary. So there is a compression member. You need to decide if it's braced, non-sway, or sideway inhibited. I think this is what the steel guys use now. I don't know. You have this case, then you have to check this formula. And if you satisfy, you are below the limit is variable, but cannot exceed 40, then you got a non-slender. If you get a value that is greater than the limit, then it's slender, right? If it's unbraced, or sway, or sideway uninhibited, right, then your limit is only one number, and so you are below that limit, is non-slender, but if you exceed the limit, it's slender. Okay. All right. Now here are some recommendations. Some people say that to avoid any slenderness effects in a braced frame, the height of the column should be approximately 6.5 times the smallest column dimension. Yes, that will give you a very non-sway case. Non-slender case, right? But it's very conservative. Okay? A much better value are these ones right here. Okay? You have the central column, you got 10 times your age. You have an edge column, 9 times your age. A corner column, because it has moments in both directions, probably, then is 8 times age. Okay? So this is kind of help you size your column. You are trying to avoid slender behavior of the columns. Okay? There. So let's use some of this material. Here is a frame, and normally, what we normally learn, right? Thick connection, pin connections. So that's typical, right? That we learn. And we have the columns. They have a 36-inch value parallel to the plane of the paper and 32 perpendicular to the paper. So the dimension of the column going in this direction is 36. And then coming out of the screen, right, is 32. Your beams are 30 inches high and 36 wide. Okay, the material properties are here for all beams, 3,000, and for the columns, 6,000. That is because lots of columns could have values that are higher than your beams. Okay? Especially you have a 10-story, 12-story, 20-story building, your columns will change in strength, and the bottom columns will have a higher strength concrete. Okay? All right. So this one is unbraced. They're telling us here unbraced. Okay. So they already did that for us. So we don't have to do that first, right? Otherwise, you have to do first the calculation for unbraced or braced. But in this case, they're telling us it's unbraced. If it's unbraced, the limit is this. Only one limit. Okay. All right. So we find LU. Okay, and has to be the clear value, right? Okay. So these values normally given like this, right, are center to center, right? So 18 feet is center to center. But you want the clear value. Okay. My column is 30 inches. So if this is center to center, that means I got here 15 inches that are below this center line, right? So 15 inches. So I need to subtract then those 15 inches from this 18 to have a clear value, right? And so there it is. So 18 times 12, 22 inches. I subtract the 15 inches, right? And that gives me my clear value for that. Right? My radius of gyration is 0.3. That's the approximate value from the code times the h. But the h is in the direction of your lateral movement. And as I said, that would be in the direction of the applied lateral load. In this case, our lateral load is in the plane, is in the direction here, left to right or right to left, right? So we're doing that. Okay. So for that case, then my h will be the dimension parallel to that lateral load, which is 36. Okay. So we use then 36, and that gives me my radius of gyration. Okay. To find k, right, I need to find my moment of inertia of the column, gross value, that's the first value, and then my beam, right? Notice where the h goes. Okay, again, this is your h, right, for the column. Right? For the beam, it was given, so that was easy. But for the column, remember, it depends on the direction of your lateral load. So I got that value. Next, I'm going to apply my 0.7 and 0.35, remember, to make those corrections on the moments of inertia. So here, my column is being modified, and my girders are being modified. Because I have different concretes, I have a modulus of elasticity for the column, and I have a modulus of elasticity for the beam. Next, we're going to find the psi A and psi B. So if we're going to do this exterior column, right, one psi value is going to depend on this condition that is fixed, right? And I already gave you the value for a fixed, right? 1. Right. But the other one here is the other psi value I need to find. Notice that at this joint, you have one column coming to the joint and one beam coming to the joint. So your psi value will have then the EIL of one beam and the one column. Okay. So I go here. I only have one column. So I put my E value for the column, my I value for the column, and my length, my clear length, my center to center, excuse me. This is LCs. So my center to center length of the column, okay, which is the 18, right? Center to center. So that's one column. And then we have one beam. So E of the beam, moment of inertia of the beam, and the length of the beam. Okay. And so that is your 25 that you have here. Okay. All right. Psi B, as I said, on the bottom is 1. And then using the chart, I'm going to go to the chart with this number and find my K value. Okay. Now, one question that you're going to be asked, you should be asking already, right? Well, why you do psi A, this one? Should have been psi B. And this should be psi A. The answer is it does not matter. Okay? One is A, one joint is A, the other joint is B. Which one you call A and B, it does not matter. Okay? And I'm going to show you that here. So this is 603 and 1. 603 and 1 and is embraced, right? So we go here to this chart, right? So 603 and 1. So let me pick a line here and make it here. So you can do 603. There's some place around here, right? And 1. Okay. So there's my one, right? So there is my value, right? I would say 1.67, 75, 74, okay, around there. Right? Okay. Now, what happens if you would have called your psi A psi B and your psi B psi A? Well, then you would have plotted the other way, right? You would have come here and say, okay, there it is, 6 approximately. Oops, did I pick it up? Maybe not. As I go here now, this is my 603, well, almost 6. I mean, so 6 again, and you're going to 1, right? Same answer, right? So that's why it doesn't matter. Okay, so it doesn't matter which one is A and which one is B. Okay. You just have to have one of the joints A, the other joint B. All right? So this explains why it does not matter how to pick A or B. Okay? One joint is A, one joint is B. That's all it matters. Okay? And so you go to the chart, you read your value, and then you have your number. All right? 174. All right? So there it is. With that, now you go to your slenderness ratio and you go 174, then your LU. Now this is now the clear value. So 201, you reduce aberration, 10.8, 32.4. That's greater than 22. 22 is the limit for braced. Therefore, this exterior column is a long column. It's a slender column. Okay, a slender column. Let's look at interior columns. Okay, interior columns. So this is an interior column, right? Now this is a pin connection, right? We know the psi value, right? 10. So we're going to use 10 here. But here at the top, you have one beam coming from the left side of the joint, right? And then you have another beam here coming from the right side, and then you have your column. So you have two beams and one column coming to the joint. It's always the number of members that are coming to the joint. You have a column coming down from here, you will have two columns and two beams. Okay. So in this case, then two beams, one column, and so here is one column, but I have two beams, one and two beams. Okay. And my value now is 302, so 302 and 10. Okay. And again, it doesn't matter which one is A, which one is B. Okay. But with 302, which is almost 3 and 10, so we do the same, right? We go to our chart, and we have to use the right chart, which is the unbraced case, right? So this one right here, with that unbraced case, we go and pick a value, and so we go from 3 to 10. So there, approximately, right? So you got then 2, 1, a little, maybe 215 again, 214. Okay. No, because this is 2, 4, 6, 8. Okay, so check your scales. Okay, so this one was okay, right? The other 1.6, 1.7, 1.8, 1.9, 2. But this one right here is going 2.2, 2.4, 2.6, 2.8. And also notice that the spaces are not equal, right? Which means that this is a log scale, right? And so that's why. So you have to be careful. So it's not equal. So yeah. So that's why you are approximating your readings. Okay? Because remember, this kind of a log scale. So really it's 2.2, 2.24. Some may say 23. Maybe even some say 25. Okay? But it's in there. All right. So that's the value that you have for your K. And so we'll do that one. Okay. And again, doesn't matter which way is A or B. And so we get our K value for that one. And we got actually 239. Oh my gosh. Well, let's see. Why is that? Oh, yes. You know why? Remember exactly what I was just telling you, right? The scale. Right? The scale, exactly. Yeah. Because this is 2.2, 2.4, right? And so 2.3 is here, right? And so, yeah, so I think it's 230, 229, I think, more like that. Let me check. So if we do that, we go from 3 to 10. Right? Okay. So 2.2, almost 2.3, right? Because that's 2.4, 6, 8, and 3. So that's 2.4. So it's not 239. I think it's 229. You want to be that precise, or 2.3. All right. And so that's your real value. All right. So let's do that one. Make a little correction here. Then this is 229 and 2. Oops, that's 229. Let's see if I can open that one. Yeah, 229. So that's going to be a little less there. So 2.29 times 201 divided by 10.8. Value is 42.6. So 42.6 is still bigger, and so that column is also is slender or long. Mm-hmm. So there it is, 42.6. Okay. All right. This is the frame that we looked before, that we look at the Q value, right? And we're going to give some dimensions to this. So all girders are 12 by 24. Let's see. And columns are not all girders, I think. Yeah, that's not right. 20 by 24 are your columns. Your beams are 20 by 26. And 26 is your height. So B first, right? And H second. So that's 26. So 20 by 26 are your girders. Columns are 20 by 24. You're going to look only at this column, EF. And somehow you did your analysis, and you got double curvature, right? And you got 2 moments in there. So here are the lengths. So we're going to do that. So let's find out what kind of slenderness we have. So EF is the second story column. And we show, when we did 10.5, right, we showed that the top story, right, was braced. So we did that using the Q index. That was your example on that one. So remember, that's the first step. The first step is always to know if it's braced or unbraced. Otherwise, you don't know which formula to use. So because it's braced, we're going to use this formula. Okay? And with that formula, I need to know the moments. Okay? So my moment 1 is the smallest, which is 104. And the largest moment, which is 2, is 130. Okay? So I got my moments. I put them here in the ratio. Double curvature is positive, so that would be 0.8. Positive, I put it here. The value happens to be 43.6. We cannot exceed 40. So the limit is 40. Okay? So if we go past 40, for this particular case, with those moments, right? Because now the limit is a function of the moments. So for those moments, and this particular case, the limit is 40. So if we exceed 40, it becomes slender. Okay, we find LU again. So we get 12, right? Minus half of the beam, which is 13 inches. And half of the beam in this direction, another 13 inches. So that's 26. Because remember, we want the clear value, right? So it's 12 minus 13 and minus 13. So that would be 12 feet multiplied by 12 to make it in inches. And then you subtract 26 inches. Oops, I went past it. So 12 times 12 to change it to inches, and you subtract 26. Half of the beam above, half of the beam below, right? That's 118. To find the radius of gyration is 0.3 times h. Okay. Again, if we are looking at buckling in the direction of the plane, in the direction of the screen, right? Left, right, right, left, the h is 24. If we're looking at buckling out of the screen, okay, out and in of the screen, the h will be 20. Okay, so with the 24, then we find our radius of gyration. Then we're going to find our moments of inertia. Both beams are the same, have the same dimension, so we get the gross value to be that. And then the gross value, excuse me, these are the columns. Yeah, so these are your columns. Your columns have this same moment of inertia, same cross-section, and the same for the girders, right? Same cross-section. So these are your gross values for columns and girders. Okay. And to account for the effect of flexural cracking, creep, and non-linearity, we multiply by 0.7 and 0.35. So what's the purpose? That's a good question for the part 8, right? What is the purpose of using a 0.7 to reduce the moment of inertia of a column? Or what is the purpose of using a 0.35 to reduce the moment of inertia of a girder? To account for flexural cracking, creep, non-linearity effects. Okay. All right, so here there are the reduced values, and then we use the reduced values to find our numbers. So this is the top joint. Okay, let's go to the top joint. So top joint of this column is this one. It has one beam on the left, one beam on the right, and only one column framing into that joint. So we're going to have two beams, different lengths, and one column getting into the joint. Okay. So we go, one column, and we have one beam with a 30 and another beam with a 24. So that's my top value, 175. Then we do the bottom one. So let's go at the bottom one, right? The bottom joint of this, you're looking at this column, right? So the bottom joint here has one beam on the left, one beam on the right, one column on the top, one column in the bottom, right? Column on the top has a length of 12, column at the bottom has a length of 16. So now we have two columns, two beams. And so we got two columns, one at 12 one at 16, and 2 beams, one at 30, one at 24. So now these are your numbers, 175 and 306. This is a braced case. This is a braced case. So we go to the chart. So wait a minute. I didn't pay attention to this. So 175 and 306. 175 and 306. Okay. So now we're going to use the brace case, right? And so again, it doesn't matter which direction we do it, right? We just need a line. So 175, so that's 1.5. Half of that will be almost 175, but remember is log, so it's a little bit more than half. So maybe here, okay, 175 to 306. So 306, it's almost 3. Okay, we're close to that. So that's my value. Okay, so what do we have? 0.8, that's 0.85 then, right? So you can call this 0.87, yeah, maybe. Yeah, I would say that's pretty good. Yeah. Your 0.87 probably is here, really. So 0.87 maybe here. So maybe this is more like a 0.865, but you don't need to get that precise. Mm-hmm. So 0.87 probably, right? Yes, good. Mm-hmm. And so we get here, and wait a minute, what am I doing? So that's the other problem. So this one. So 0.87 we found that, yeah, 0.87. Okay. So 0.87 times the clear value, don't forget, right? Divided by your duration, that's 14.3, is below the 40, column is short, okay? Or non-slender. Now, notice that in the case of the braced cases, right, the non-sway cases, for the non-sway cases, the maximum value that you can get is 1. Anything else is going to be less than 1. So a lot of people, to avoid doing lots of calculations, right, what they do is they assume a k value of 1. If you use a k value of 1, right, and it passes, so it becomes non-slender, then whatever you pick, the actual value is going to be even better, right? So then you're done. Okay? So in other words, for a brace case, right? For a brace case, if I don't need to know exactly what the slenderness is, all I need to know if it's slender or not, right? Then I can save myself the headache of finding this and finding all that, right? All I need to do is simply come in here and say, I'm going to assume a k value of 1. And since I know already my 118 and my 7.2, I do 1 times 118 divided by 7.2. That number is 16.4. 16.4 is below 40, so it's short. And I saved the time to doing all these calculations because this number is going to make it even better, right? And so assuming a 1 and it passes, then you save a lot of time. If it doesn't pass, then you may want to try to find the actual value because it might be that it's very close and it actually passes with the real number, right? So that's very common then to use a value of 1 and just to do a quick check because it saves time. Now, here they are going to check column DE, column DE, and they're giving us the moments. So moment at E is 125, D is your pin connection, so that's a 0, right? So now we're going to go and do DE, okay? Notice that the psi value that we use for the bottom of this column is the same value for the top of this column, all right? So we already have the number. We already found the psi value for the top. The psi value here is a pin connection, so we know that is a 10, right? So that means then that we know the psi values already. Okay? So 306 and 10. And the bottom part of the frame, remember when we did the Q index, right? That was unbraced. So now we need to use the unbraced case. And so 10 and 230, excuse me, 3 and 10, right? So 3 and 10, let's see if I did this right. So now we have 3 and 10, and come in here. So we got a 3 and a 10. Right. So again, that's 2, 2.2, 2.4, 2.3 will be very close here. Yeah, it looks like we're doing the same thing at 229, right? So at 229 there. Okay. So, or 2.3, I mean, that's okay. So let's see what I did. So we're doing this one, 239. 230. See, I like this 239. I don't know why. Yeah. So it's 229, right? 229. And so the unsupported length again, 16 times 12. Now in this case, your pin value is right here at the bottom, or usually it's at the bottom of your column. So the only thing you need to subtract is one beam, half of the beam depth, right? So that means you need to subtract 13 inches to get your clear value. Okay, your clear value minus 13 inches. So we do the minus 13 inches, that gives us that number. And then this one again is 229. And so 2.29 times 179 divided by 7.2, and the value is 56.9. Okay, 56.9. Oops, I need to do that. So 56.9. So 56.9, there it is. All right, so 56.9. And still, I mean, it's long. Okay, so this is slender. Right. So now we got non slender on the top, slender at the bottom, right? So different cases. You can see that columns can have different cases depending on where you are in your building. Okay. So that way you had to check all of them. So you cannot just do, I'm going to check one column, I'm done. No. You had to check any column that had any differences in heights, difference in cross sections, right? Different moment conditions, because the moment conditions can change your slenderness, right? So that needs to be done. Okay, so I'm going to stop here, and